Okay. So welcome to the February 7th, 2022 Yaskawa Monday Morning Industrial VFD Training class. And it occurs to me that we're 7 days away from Bear Trap Day, which is the day that you have to remember, because if you forget it, your significant other is going to throw you into a bear trap. So I have that on my calendar. I've always thought that Valentine's Day is a no-win situation for me, because you have to do something, and if you forget it, you're in the jailhouse. But 7 days away from Valentine's Day and the second month of 2022. And today we're going to continue the discussion from last week, where we started talking about the Yaskawa matrix drive, and we're going to talk today in depth about how the matrix drive generates the input and output waveforms, or controls the input and generates the output waveforms. And we want to start by looking at what we know as a basis point to get some perspective, and that would be the PWM drive. So let me share the screen. And go to okay, so I take it, wait a minute. This is the thing about multiple screens. I'm not sure which one you are seeing. Are you seeing the full screen, Danny, or are you seeing the screen with all the other images on the left?
Yeah, this is the one with the images on the left. You should be able to, when you go to share, it should open a window that shows if you're in display mode, or show, it should show that screen as well.
It did do that. Unfortunately, it opened it in the wrong screen. So let me just take a moment here and figure this out. But today we are going to talk about not only how the PWM of a conventional drive works, but how we still PWM, but with no DC bus on the matrix drive, we're sourcing directly off of the AC line to get our voltages. And the thing you've got to remember is that the AC line is constantly varying, as opposed to the DC bus, which is a constant voltage. The matrix drive knows what the AC line is doing at all times. The conventional drive does not. The conventional drive's electronics, sensors, etc., are separated from the AC input line by a big diode bridge. And hang on a second, I gotta, there we go. I needed to mute somebody. So unless we have voltage sensors on the input, we don't see the incoming line, and it's not relevant to the way that a conventional PWM drive works. So how do we get an how do we sense over voltage on a conventional PWM drive? Well, we don't sense the incoming line, as I said. So what we do is we sense the DC bus, and the DC bus is a reflection of the input line, but it is only a reflection. So we see a level because it's DC, and we can react to over voltage, but we cannot see the individual phases of the incoming line. The matrix drive can do that. So I'll figure that whole thing out with the presentation later, but I think you guys can see this screen relatively well. So let's start with the matrix drive versus conventional drive architecture. This is a review for everybody, of course, but here's my DC bus, right? Positive rail, negative rail, and somebody tell me if you can see my cursor.
Yes.
Okay, thank you. So here's your incoming line. Here's that separation I was talking about, the diode bridge, and this is what the control board on the conventional PWM drive can see. Now let's go back to some real basics here. We are trying to control a motor. It is an AC induction motor, and in an AC induction motor, current is torque. What are we really trying to produce on the output of that motor? Torque. Therefore, we're trying to control current in the motor, and our only method of controlling that is voltage. So here's the AC line. We've already said we can't really see it, therefore we can't control anything from that. We make it into a DC bus, which is a constant voltage. And then we use this 6-transistor H bridge to pulse this voltage out to the motor, controlling voltage to create a desired current. But we only have one level of voltage to control, and therefore the only thing we can do is control the time on and time off that we apply that voltage to the motor. And I'm going slowly because I want this to sink in. This is, if you understand these basic concepts, understanding a PWM drive becomes very easy, and therefore understanding the matrix drive will become easier. So here is what we can do with our pulses. This is the charge pulse coming off the DC bus. I apply it to one phase of the motor, and here's what happens in the motor as far as current is concerned. I get a rising current. Why do I not get a similar shaped current as the voltage? And that is because the motor has inductive reactance. An inductor is a current shock absorber. Same way a capacitor is a voltage shock absorber. So in a current, in an inductor, there's a charge up time. And from the immediate application of the voltage, we don't jump to full current. We start to ramp up based on the charge up time of the inductive reactance of the AC motor. So here's what happens with each pulse. Now, if we take each one of these and we start to build a sine wave out of it, we're going to pulse. And when we stop pulsing, we fall to zero, right? But if we don't want to fall to zero, we'll start the pulse here for the next one. The off time is what we control. And therefore, the inductor will fall so much. And then as soon as we start the next phase, it starts to charge up again. As we start to climb the slope of the sine wave that we want to produce in the motor, current sine wave, so that we can produce sinusoidal output torque on the motor. Over here, this is a full phase of pulse width modulation. These are the individual pulses. But here, the current would climb, peak, and then start to descend. And that's the sine wave that we're talking about for the current in the induction motor. Now, just a little side note here, because when you actually look at this on a scope, you're going to see this, okay? And this is not represented here. That little spike comes from the flyback diodes around the transistor. So I don't want you to be confused when you look at a scope and you say, what the heck is that? Yeah, these PWM drives are noisy, aren't they? But you can see on this scope the rise time, and then you see this thing going on here. What's that? Well, the inductor doesn't immediately react when the current or when the voltage shuts off. Remember, it's a current shock absorber, so it's going to ramp down again the same way that it ramped up. This portion here is due to the inductive reactance in the motor. This is due to the flyback diode in the circuitry of the H-bridge. So here is what I'm talking about. We're building a current ramp by pulsing. Now in this example, the pulses are all the same size. That's not what we do in a drive, because in the drive we want to ramp up and then we start to thin the pulses when we want to ramp down again. But here you can see that with the leading edge of the pulse, we start to get a rise in the current. When the pulse turns off, the current starts to degrade. Again, ignoring that flyback diode portion, we rise and we fall. So if we don't want to fall all the way back to 0 again, then we control our off time and we start the next pulse here, preventing a total degradation to 0 of the current, and we continue on our path up on the first half of the sine wave. Are there any questions on that? It's very important that you understand this basic concept, because when we go to this, now you can see why we pulse width modulate. At the highest point of the sine wave that we're trying to create in the motor, our pulses are going to be widest. You can see that in this rudimentary example. You can see this in this actual representation of a scope trace. Here, you don't see the sawtooths because this is a diagrammatic representation. Here, you see the sawtooth of the decay. Now, the conventional PWM drive has current sensors, and therefore we use that current feedback to modulate the only thing we can modulate, which is the pulse width and the resultant off time of the pulses, in order to simulate the current waveform we want in the motor. And it's quite effective. I mean, we've been doing this since 1983. This circuit works. We're out there controlling a bunch of motors. Yes, there are some deleterious effects of this in terms of the noise, etc. DVDT to the motor. But with a close to $2 billion market for variable frequency drives in North America alone, it works. As we said before, we hang a bunch of filters on this to correct it, etc., but this is basically what we're doing. Okay. The matrix drive can see the line. At any given moment, you've got a selection of voltages that you can choose to switch directly to the motor. This is the electrical representation of the power circuit of the matrix drive. Note, we connect the AC input directly to the motor. That's a very important thing to understand here because we're not using that DC bus as a buffer. At the time that we developed the pulse width modulated drive, I say we in the great collective we because I wasn't personally part of it, the DC bus was necessary because we didn't have the sophistication to switch directly from a dynamic 60 hertz plus or minus a couple of hertz line at 460 volts plus or minus whatever voltage variance is going on, plus all the harmonics on the line. We didn't have the sophistication to react to that and jam that directly into the motor the way we wanted to. So we basically designed a circuit to white out the AC line and make DC, and then we're dealing from a constant DC bus. We put big capacitors on it to make sure it was constant. And then with the simple 6 transistor H bridge of the PWM drive that we showed you earlier, the fact is that we could then switch using the limitations of our circuitry of the day and create nothing more than a control of on time and off time. Very simple to do. The initial VFD that did this in the United States market was the Toshiba VT130G1. It didn't even have a processor. It was an analog circuit board that was just creating pulses. The Yaskawa unit that came out in 1984 in the United States actually employed a processor. So it was the first digitally controlled PWM drive. But Toshiba has the honors for the first PWM drive. Now, because we could not directly touch the line and deliver it to the AC motor, we employed the DC bus. The matrix drive does not need a DC bus. So we've eliminated some pretty significant power components in the structure of the matrix drive, the power capacitors. And that, by the way, increases the reliability of the matrix drive. The power capacitors are not the most reliable power component in the circuit. Although with time, they've certainly improved. Nevertheless, we have no DC bus in the matrix drive. Note this because this is also a limitation in certain applications. You do not have the ability to battery back up the DC bus on a matrix drive because there is no matrix drive DC bus. So certain applications, such as a battery backup or running from a DC source, as we might on quite a number of mobile vehicles, is not possible with a matrix drive. What is also not possible on a matrix drive is to share power on the DC bus because there is no DC bus. However, because the matrix drive does regenerate back to the line, you can use the line as a power sharing mechanism. So in the case, for example, where you would have a winder, let's just call it a converting line, where you have an unwinder and a winder. The unwinder is going to have material pulled off of it by the winder, and it's going to resist that pulling in order to create a certain tension on the web of material that is necessary for whatever we're doing to that material in between the unwind and the wind. That's not relevant to this discussion. What's relevant to this discussion is I'm unwinding and I'm winding up. The winder is going to pull power from the line as it tugs the material from the unwinder that's resisting that pulling force. And therefore, the unwinder is going to regen. When I do winder-unwinder with a standard PWM drive availability, I just connect the DC buses. When I do that with the matrix drive, that power circle is completed through the line itself. So let's start to dive into how we use our variable voltage bus to apply the correct phase-to-phase voltage to the motor. What hasn't changed here is that we're still using voltage to create a certain desired current waveform in the AC induction motor. That hasn't changed. Controlling voltage to get the desired current. So if we have the ability to track the AC line, we have the ability through this circuit to pick off several voltages at any given moment and directly apply them to the winding of the motor. We're still going to depend on the inductive reactance of that motor to smooth out the resultant current. But because we're not hitting the motor with full voltage pulses, we have a bit better ability to shape that current waveform. In addition to pulse width modulation, we have a rudimentary pulse amplitude modulation, and as you'll see later, it's a 3-level pulse amplitude modulation. With pulse width modulation, in both types of drives, we can control the pulse width almost infinitely to an infinite resolution. But with the pulse amplitude modulation in the matrix drive, you will see we only have 3 different selections. And nevertheless, that has a significant effect on our ability to properly shape the current waveform to the motor. What you will also see is it has a significant impact on our ability to shape the current waveform that we're pulling from the line, and thus the matrix's ability to have a very good harmonic distortion signature reflected back to the AC line. And that's a major advantage of the matrix drive. But again, we can't do that with the conventional drive because the conventional drive, again, I'll page up to this diagram up here. Our control ends here. Anything we do on our control boards is only affecting this portion of the circuit. I have no ability to affect this portion of the circuit with any dynamic control coming off the control board of the conventional VFD because of this diode bridge. Therefore, the current waveform that results here is based on the nature of these passive check valves, these diodes. These diodes are not controlled. You forward bias them by putting a higher voltage behind them than they have in front of them, and they will conduct. And thus the current waveform here isn't affected at all by our control board, and it's not very good. As you know, current harmonics on a VFD without any filtration here can be as high as 80%, and they're required to be less than 5%. That's distortion. So with the matrix drive, because we have a direct look at this line, these switches not only control current going this way, but these switches can control current here as well. The matrix drive, without the inductors, etc., that we use to filter the input of a regular drive, the matrix drive can achieve 5% distortion on the current waveform. Similarly, because it's a circuit that looks the same both ways, it's the two-headed llama, we have a less than 5% current distortion on the motor as well. We are producing a 95% accurate sine wave to the motor. So, any voltage that we want on the AC line that is available, we can then directly apply it to the motor via the matrix control. Here is how a PWM drive generates its pulses. Going back to the traditional drive. We generate a control waveform in the logic, and that triangular waveform basically goes up and down, up and down, up and down at the carrier frequency of the switching rate of the transistor, of the power transistor. Now, this waveform is not generated on the power sense. It's generated in small voltages on the control board. And in truly digital drives, it's just represented virtually or generated virtually. But it does trigger, as you can see, the turn on and turn off and resultant off time and turn on of the next pulse. So the reference sine wave determines when we turn on and turn off when it's overlaid on top of this triangular waveform. And you can see the concept's relatively simple. And it needed to be because in 1983, we didn't have a tremendous amount of processing power to control our H-bridge. Today, we can do much more sophisticated things, but this is still the basic way that the PWM traditional drive is controlled. It's how we generate the PWM signal. Because we only have one voltage to switch from, all these resultant output pulses of the H-bridge of the traditional inverter are the same. When we go to the matrix drive, we can select all sorts of different voltages from the AC input. And thus apply them the way we want on the output. Now, those of you that are in my age bracket might remember the old 6-step SCR drive. And in today's level of technology, it was certainly somewhat primitive, but it did control the voltage level to the motor. And indeed, look how we are controlling that voltage level in what looks like this is a 3-step, but when you look at the reflected negative side of the sine wave, it's going to be a 6-step. And so we've gone back to 6-step technology, which I find to be very interesting. So when we look at the output waveform to the motor, we're getting this instead of one single pulse height. This level here is equivalent to the DC bus of the old technology. So let's take a look at what an actual oscilloscope read looks like. And you can see this sort of looks like a PWM waveform. But if you look closer, every one of these pulses is not up the one side to the full level and down the other side. Every one of these pulses, if we blow them up, is the 3-level pulse. First level of voltage, second level of voltage, third level of voltage. And we can control those and apply those to the motor in a way that gives us the desired current we want. And because we have not just pulse width modulation, but now 3-level pulse amplitude modulation, we have better current control. And therefore we have better torque production in the motor. Smoother operation, better efficiency. One of the benefits is that we reduce the DVDT to the motor because we're not jumping from 0 to a 700 volt DC pulse height. which would be what the DC bus is on a conventional 460 volt drive. 480 volts rectified is about 683 volts DC. It's a square root of 2 relationship. AC times the square root of 2 gives you the resultant DC when you're using a full wave bridge rectifier. So we don't have to blast the motor. Now, let's say you're using a 5 kilohertz carrier frequency. We don't have to blast the motor 5,000 times a second with a full pulse height in voltage and the resultant spikes that are associated with that, because you always have a spike on the leading edge of the pulse. So 5,000 full voltage pulses to the motor. This has caused innumerable problems in the past that we've used a lot of passive filters for. In the matrix drive, because we can start at a lower level, then switch to the higher level, then switch to a lower level and down to 0 again on individual pulses, we actually reduce the DVDT to the motor by about 30%. It means that if we are trying to protect the motor on long lead lengths, we needn't use as much of a DVDT filter, because we're not trying to absorb as much spurious, undesired spike energy. We still do want to apply a DVDT filter in many long lead length applications with the matrix drive, because we still have PWM coming off of our pulses. It's just not nearly as severe, reduced by 30%, as the PWM coming off of a constant DC bus. Now, oops. This next slide, I'm going to show it. I don't really like it, but basically what we're saying is that the voltage that we apply to the motor is premixed in the DC bus of the conventional drive, and in the matrix drive, we mix the voltage dynamically. If this works for you, okay. Sometimes the fluid analogy is very effective in explaining electrical principles. In this case, I'm not real convinced of it myself, but if this works for you, that's great. This is a Yaskawa presentation, by the way, that I've added a few things into. So let's look at a scope trace. On the top, you have your input voltage. That's what the power company gives us. And on the top, you have your input current for the sine wave. I'm sorry, for that is sinusoidal with the matrix drive. We all have seen the traditional 3-humped camel input current waveform that comes from the full wave diode bridge of the conventional drive. And that is undesirable. This is very desirable. This is without significant inductors on the front end of the matrix drive. And while we're on that point, I'm going to jump back here, because everybody always says, wait a minute, you're representing the matrix drive, and you see, I see a filter here. This filter is a very small filter. It's an EMI RFI filter. It's basically there to trap high frequency noise going back to the line, the switching noise of our transistors. Because our transistors are directly connected to the line, and in the conventional drive, the transistors are not, the noise of the transistors reflects back into the input line, and we use this filter to suppress that. Many times you will use an EMI RFI filter on the input of a conventional drive as well. But in the case of the matrix drive, because of the direct exposure of the transistors, we incorporate that in as a standard. This is not a current filtering massive amount of iron and copper. I need to clarify that. So, very nice current waveform, compliant to IEEE 519 in pretty much any application down to 30% of load. Again, this is what we're given. This is what we're trying to control, both on the input and the output. And notice the matrix drive does a very nice job in both cases. The output voltage, this is a confusing waveform. Why doesn't it look like this? Well, because the fact is that when you break this down, this is what you're seeing in the little pieces. And so you see this sort of almost three-phase sine representation of this PWM as opposed to the standard PWM of a traditional drive, which is just flat topped. So when you look at it on the output voltage of the scope, you can see those ghosting traces of the sine wave from our three-step output to the motor. And that's a diagrammatic representation of it. Again, the three-step waveform here. Now, this presentation from a sales standpoint is very effective, although it's Gargunda. So you have ability to access this presentation in its 300 megabits of glory. You can't email it, but go to your Teams site and you can use it from there when you're doing demonstrations in front of the customer. Basically, if you hover over it, you get the on button and you can play this video. This is a real scope choice. Now, we just turned on, right? And we started outputting to the motor. There's our voltage waveform with those ghosted sine wave representations, basically the three-level voltage output. Here is our current waveform at a much lower frequency than the input line, of course, because we're just starting to ramp up. But as we increase the speed, amplitude of the current waveform goes up and the frequency of the current waveform goes up. More amplitude, more torque. More frequency, more speed. And there you have a real-time scope trace, which proves categorically to anybody with a decent understanding of electricity that we reflect a very nice current waveform back to the line. We have a beautiful current waveform going to the motor without filters. Again, footnote, the little EMI RFI filter on the front end. It's hard for people to understand the matrix drive and how significant a product advancement it is. I have probably as much perspective as anybody on the modern VFD technology development, because myself, as well as several other people in our organization, have been with it since this, since '79. So I get it. This is a huge change, but there's an evolution behind it that I get. when you present the matrix drive to someone who doesn't have the understanding of the technology history, they're going to look at you and say, that's really new. I don't know that I want to be your guinea pig. And therein lies the rub in terms of selling matrix to a community that has been using a different type of drive forever and has learned to live with the issues associated with that different type of drive, and that's their comfort zone. We run into this all the time when we try to go to a water utility, for example, very conservative organization, high downtime risk, lots of dollars involved, and nobody in those organizations is interested in threatening their pension by taking unnecessary risks. Nobody ever got fired for specifying Allen Bradley, is the old saying. So as we switch now from a deep dive technical explanation to a more human emotional sales discussion, we really do have to recognize the position of the person we're talking to, the person we're trying to convince to use the matrix drive. And tools such as this oscilloscope are very, very important. I'm not a head shrinker. I'm not real good at people that are extremely emotional in terms of, dealing with them and having them do what I want them to do, as is evidenced by my interaction with my children at certain moments. But the fact is that I use facts and data and hopefully come across as being truthful when I present the matrix drive to potential clients. And I'm aware of the fact that that engineer that I'm talking to, who's about to specify 5,000 horsepower worth of VFDs, is going to have all kinds of issues that he's already comfortable dealing with. Whether he's going to use an 18 pulse front end or a whole bunch of fancy DVDT filters, or maybe he doesn't really care about IEEE 519. And on the output, he's got an AC reactor or even a sine wave filter to protect his downhole submersible pump motor or his big turbine pump motor. This is something he's done for the last 15 years. The specification is written around it. And it's a pretty significant sales challenge to change that. You do it one step at a time, as the old saying goes. And we have some ability to give you references from some pretty significant end user customers, such as Los Angeles County Sanitation District. Or in the case of the industrial arena, several large converting companies. In the case of the oil patch, we've got thousands of matrix drives on the downhole beam pumps. And when you get into the higher flow wells, water or oil, and in the case of oil, it's mostly water anyway. They say that the cut of what you're pumping out of an oil well, 6-7% oil, the rest of it's water. So those applications are very much the same. But we have a significant installed base of matrix drives out there. So use that as well. But this tool, to show the customer exactly what he's getting, I find to be very effective. Here we go up to speed. And we're off. So in the last 10 minutes or so, I want to give you the negatives on the matrix drive, because you need to be aware of those too. Matrix drive, while much closer to perfection than the original PWM transistorized drive, still has its limitations. We are still seeking the perfect electric valve. But in the case of the matrix, you need to be aware of a couple of things. The matrix drive, because its lack of DC bus and that big capacitance, doesn't have the same energy storage available to it to react to highly dynamic situations, and in this case specifically highly dynamic loads on the AC induction motor. As a result, when you're talking about high impact loads, I want to be in that conversation with you. I want to help you size the matrix drive properly. This is not a defeating circumstance. This is a circumstance that needs to be properly engineered. And we may oversize in those circumstances once we understand the dynamics of the load. But in dynamic load situations, we cannot just go ahead and apply the matrix drive without reasonable analysis. So that's point number one. Point number two is the matrix drive compared to a conventional drive is more than twice the cost. So we're going to have to be going after applications that justify the extra cost. And obviously, what we want is a situation where the matrix drive is less in cost than the associated solution that uses a conventional drive. And in those cases, we immediately get a foot up when we have to comply to IEEE 519, because complying to IEEE 519 for a conventional drive is going to pretty much double the cost of that drive, getting it close to the cost of the matrix drive. And now we're dealing with the input end, this green waveform on this oscilloscope. That comes with the matrix drive, and it requires you to just about double the cost on a standard drive to achieve it. However, we're also concerned about the output waveform. And the output waveform, if you want that to be sinusoidal as well, especially in long lead length applications, the matrix drive delivers that without filters as well. So applications that require a sinusoidal output to the motor are advantage matrix drive, because you have to add even more cost to the conventional drive. A sine wave filter on the output of a conventional drive, whether you buy from TCI, MTE, or any of their competitors, will just about double the cost of the VFD as well. So if we're talking about circumstances where we require sine wave current on the input and sine wave current on the output, the matrix drive is now significantly less expensive than the conventional drive with big filters on the front end and big filters on the back end or the motor side. What applications would require that? Most significantly, any long lead length applications, and especially long lead applications on non-NEMA motors, such as the downhole submersible pumps, which is a monster industry in the oil and water industries, on oil and water markets. Lots of downhole submersible pump motors. In the oil patch, down to 10,000 feet. In the water industry, 1,000 feet. Significant lead length, significant problems, significant cost advantage to the matrix. And we've talked pretty much about the conventional diode front-end drives. You know from previous discussions in this class that the active front-end drives have a much better performance because there are two inverters, one pointed at the motor, one pointed at the line. Let's just in the last few minutes briefly talk about how we compare those situations to a matrix drive. The active front-end drives are still sourcing from a common DC bus. When I say common, it's common to the input inverter and the output inverter. Therefore, the DVDT going to the motor is the same as the good old conventional drive, and that same DVDT is going to the line. So these, the AFE, the active front-end drives, require filters that, again, the matrix drive doesn't require the same degree of cost. And therefore, the matrix drive has a slight cost advantage to the active front-end drives. If we go back to the parts comparison, the matrix drive is basically 9 two-way switches. The active front-end drive is this times 2. There's no diode bridge on an active front-end drive because this is flipped around to face the line. So a lot more components, still a significant number of power capacitors, and that compared to the very simple and clean circuit of the matrix drive. So in summation, the matrix drive is the future. It's the best technology step forward we have. We're also the only ones that have it. The other companies have seen fit to advance from the diode front end 6 transistor H bridge level of technology to the active front end technology. We at Yaskawa have an active front end technology also. It's called the D1000. You made it up with any of our drives. But this is significantly superior to that technology in most of the applications that require regen or long motor lead length. There is not a lot of advantage for the matrix drive versus active front end in terms of complying to IEEE 519. There, we're pretty much toe-to-toe. So, I hope that you've had the realization that understanding matrix technology just isn't that hard. If we understand the basic dynamics of creating a voltage to create a resultant current waveform, and the fact that we do it relatively similar manner, the only thing that differs from the conventional way of doing it with the standard pulse heights of the voltage is the fact that we get to do 3 levels of voltage. These concepts are not that hard. And once we break it down into the individual parts, any technical problem, no matter how complex it might seem, is nothing more than assemblage of a lot of really simple concepts. And that is indeed what the matrix drive is. And yet, it has manifest benefits in the world of controlling motors. And by the way, the matrix drive does have a PM motor capability, PM motor control capability. I heard the other day that Grundfos, a significant player in the submersible pump market, has introduced a PM submersible pump, which is, in my opinion, a significant bellwether of where the markets are going to be going. PM motors are coming in a big way, and we're already seeing them in many applications. If they now start to show up in the major markets of fluid movement, then our ability to control PM motors becomes a significant competitive factor. So note that the matrix drive does come with that capability, as does the GA500 open loop, as does the GA800 in open loop and closed loop. So in the last couple of minutes, are there any questions? Is there anything that you're not quite sure of? By the way, this presentation is on your site, so you can download it. The one that's on the site now doesn't include the additions that I made for this presentation today, which are primarily these, and I will update that and put this presentation on. But are there any questions that you might have with regards to what we've gone over today on the matrix drive? Okay, well, with that, I have a long drive, so I got to get going. I appreciate your time and attention. I hope this has been valuable. But it's 7:59. It's time to go to work, and I got to get on the road. Thanks a lot, and we'll see you next week.
Thank you, Pierce.